somewhere on the outskirts of Shanghai, a cleanroom that costs several $billion and roughly a decade to build is running silicon through a process that, until recently, only one Chinese company had proven it could execute. That company is Hua Hong Semiconductor. The process is 7-nanometer multi-patterning on deep ultraviolet light. No extreme ultraviolet required. No access to the machines that remain comprehensively blocked from Chinese buyers. The first test customer loading wafers into that line is Biren Technology. The graphics processor startup that United States export controls were specifically designed to freeze out. Two sides are already fighting over what this means. The bulls say China now has a second independent 7-nanometer recipe, a redundant supply chain no single sanction can sever. The skeptics say a fab producing only several thousand wafers a month by end 2026 is not a supply chain. It is a science project that has not yet survived contact with demand. 3 rounds decide it, and the round the optimists lose matters more than the one they win. The restriction was designed to make this contest unwinnable for China, to prevent the country from acquiring enough process knowledge that a second derivation was even possible. Hua Hong's clean room is evidence that the design failed on its primary objective. Whether that failure is strategically decisive or strategically marginal is the question the rounds have to answer. The 3 disputes in order: what the achievement actually proves, what the volume actually allows, and whether process knowledge compounds into capacity or stalls there. Hua Hong has independently reproduced a 7-nanometer process node using only deep ultraviolet lithography, the older, export-legal generation of chip-making light, without access to extreme ultraviolet machines. The significance the bulls attach to this is structural, not merely technical. When teardowns of Huawei's Kirin 9000S chip were published in late 2023 and confirmed that SMIC had achieved a 7-nanometer result on deep ultraviolet multi-patterning, the world learned that the technique was possible in China. What that first confirmation did not settle was whether the recipe was transferable, whether a second engineering team at a second facility with a second set of tooling configurations could arrive at the same result independently. Hua Hong's line answers that question. A second independent derivation of the same capability means the knowledge is not locked inside one cleanroom or one team of process engineers. In the language of manufacturing, it has become a reproducible result, and reproducible results do not get unreproduced by policy. With Biren Technology as a reported early customer, the process is being validated not on test structures, but on a real, complex graphics processor class design, which is a meaningful stress test. The bulls argue that 2 7-nanometer fabs, operating independently, represent a qualitative shift in the baseline. Even an aggressive expansion of export controls cannot unteach what 2 separate engineering organizations have now separately learned. The skeptics grant the technical achievement and immediately redirect to what it proves about industrial capacity versus what it proves about chip-making knowledge. Reproducing a process recipe in a second fab does not double China's 7-nanometer output. It adds a pilot line to an ecosystem where the primary facility, SMIC, is already supply constrained. The question, in the skeptical framing, is not whether Hua Hong's engineers solved the multi-patterning problem. The evidence suggests they did or are close. The question is whether a second solved problem, running at demonstration scale volumes, changes anything for the companies trying to buy leading-edge silicon in China. On that question, the skeptics have a direct answer. Not yet, and possibly not for years. Hua Hong's history matters here. The company built its reputation on mature nodes, the 40-nanometer, 55-nanometer, and 65-nanometer processes that power analog chips, power management components, and radio frequency devices. Its customer base was, until recently, almost entirely mature node. The 7-nanometer push represents a deliberate strategic pivot, reportedly encouraged by Chinese state industrial policy, rather than an organic evolution from an existing advanced node business. Reports from the semiconductor industry press, drawing on supply chain sources, indicate the new line is an early production ramp as of mid-2025, with Biren among the initial customers. No independent benchmark of Biren chips produced on Hua Hong's node has been published, so performance parity with SMIC's 7-nanometer output or with global 7-nanometer standards cannot be independently confirmed. The company's own disclosures reference the advanced node investment without specifying yield targets or capacity timelines in granular terms. What is documented is the capital commitment and the customer relationship. The process quality at volume remains the open variable. Round one to the bulls, but on narrow grounds. A second independent 7-nanometer recipe is a real achievement, and the Biren customer relationship is a real validation signal. The victory is on the knowledge dimension, not the supply dimension, and that distinction is the entire dispute. Even at low initial volumes, Hua Hong's fab is generating something the bulls value above wafer counts. A second supply relationship for Chinese chip designers who currently have no fallback if SMIC faces disruption. Biren and any other fabless company using Hua Hong's node is building a second source, which is standard practice in global chip procurement and a form of risk management that the United States export control regime has inadvertently made urgent. The bulls also reach for history. Every high-volume fab in history started at low yield and low throughput. TSMC's early nodes, Samsung's initial thin-field effect transistor ramps, SMIC's own 7-nanometer genesis, all began at volumes that the skeptics of the day would have called insufficient. Volume follows yield, and yield follows process maturity. The argument is that Hua Hong clearing the process threshold is the inflection point. The volume trajectory bends upward from here. The skeptics bring the number, and it is a number that is hard to adjudicate away. Reports from industry analysts and trade press suggest Hua Hong's 7-nanometer line is expected to reach only several thousand wafers per month by the end of 2026. SMIC's overall output is measured in hundreds of thousands of wafers per month across all nodes. Even SMIC's advanced node capacity, which is itself constrained, dwarfs what Hua Hong is projecting at its most optimistic 2026 milestone. The skeptics argue that framing this as a second front requires accepting that a front with that level of firepower changes a battle's outcome. At these volumes, the argument goes, it does not. The wafer count framing deserves unpacking because the skeptical case depends on it entirely. A wafer is not a chip. Depending on die size, a single leading-edge wafer yields between a handful and several dozen chips. Graphics processor and artificial intelligence accelerator dies are large. The kind of chip Biren designs occupies substantial wafer real estate. Several thousand wafers a month at those die sizes translates to a chip supply measured in the tens of thousands per month, at ceiling. The global artificial intelligence accelerator market, even the Chinese domestic portion that cannot access NVIDIA's export-controlled H100 and H200 products, runs on supply chains that move orders of magnitude more silicon than that. Hua Hong's 7-nanometer output, at projected 2026 volumes, is not a supply chain. It is closer in scale to what the industry calls a risk production run, enough to validate yield, characterize the process, and demonstrate real-world performance, but not enough to fulfill a significant commercial order. One important qualifier, the several thousand wafers per month figure, comes from analyst estimates and trade reports, not from Hua Hong's public disclosures. The company has not published a specific capacity ramp target for this node, which is itself informative. Fabs that are confident in their ramps tend to advertise them. Round two goes clearly to the skeptics. Several thousand wafers per month by end 2026 is not a second front. It is a second data point. The bull's historical analogy that every large fab started small is accurate, but incomplete, because every large fab also had a credible scaling pathway and the tooling access to execute it. Whether Hua Hong has both of those is exactly what the third round has to settle. The optimists make their most important argument here, and it is the one that the round two loss cannot simply absorb. Process knowledge in semiconductor manufacturing is the scarce resource, not floor space, not capital, not even equipment within limits. A fab that has solved 7-nanometer multi-patterning on deep ultraviolet light has crossed the threshold that takes the most time and the highest failure rate to cross. Scaling that process to higher volumes is an engineering and capital problem, not a physics problem. Floor space can be built. Older deep ultraviolet tools, The ASML machines that sit below the export control threshold can reportedly still be procured, though with increasing friction. Process engineers who have run a working recipe can train other engineers. The bulls argue that the hard part of what Hua Hong has done is not replicable by capital injection alone. It required time, talent, and iteration. The volume problem, by contrast, is solvable with money and determination, both of which the Chinese state has demonstrated it is willing to supply. In their framing, the relevant question is not what the fab produces in 2026, but what it produces in 2028 or 2030, and whether the process recipe now locked down gives it a credible path to that scale. The skeptics accept that process knowledge is the hard part, and then introduce the constraints the bull's scaling argument tends to skip. Deep ultraviolet multi-patterning at 7 nanometers is equipment intensive in ways that volume amplifies, not dilutes. The technique requires running wafers through lithography steps multiple times, sometimes 4 or more passes for a single critical layer, which means each additional wafer consumes disproportionately more tool time than a mature node wafer would. Running a 7-nanometer design through deep ultraviolet multi-patterning is something like photocopying a document by running it through the machine 4 times and manually aligning each pass. The output is readable, the process works, but the machine that resolves it in one pass will always produce more copies per hour. At low volume, the difference is manageable. At the volume of a real commercial run, the cost and time gap between the two approaches becomes the business case for switching. Scaling volume requires scaling tool capacity, which requires procuring more deep ultraviolet machines. Those machines are not banned, but they are scrutinized, and ASML's ability to service advanced configurations in China has been constrained by Dutch export policy changes since 2023. Yield at low volume and yield at high volume are also different problems. A process that holds together on a few thousand wafers a month may develop systematic defect modes under the thermal and contamination stress of higher throughput. And the competitive clock is not stopped while Hua Hong scales. SMIC, which has a head start of at least a couple of years on its 7-nanometer recipe and a substantially larger installed base, is itself pushing yields higher and costs lower. Hua Hong's scaling challenge is not a static target. It is a moving one. The multi-patterning throughput constraint is the most concrete of the skeptical arguments and deserves the most scrutiny. In conventional single-pass deep ultraviolet lithography, a machine exposes one layer in one pass. Multi-patterning for 7-nanometer features can require decomposing a single design layer into multiple separate mask exposures, meaning the same tool must be used repeatedly to pattern what a single extreme ultraviolet pass would resolve in one. Industry observers and equipment analysts who have described this dynamic publicly, though not specifically for Hua Hong's line, note that a deep ultraviolet-based 7-nanometer process can require substantially more tool passes per wafer than the same node on extreme ultraviolet would. That has a direct throughput consequence. A given number of deep ultraviolet tools produces fewer 7-nanometer wafers per month than an extreme ultraviolet-equipped fab would under comparable conditions. TSMC, Samsung, and Intel have all migrated leading-edge production to extreme ultraviolet precisely because of this throughput and cost per wafer dynamic. Hua Hong is running the older playbook by necessity, and at scale, that playbook is more expensive. The bull's response, that Chinese state subsidy can absorb the cost premium, is plausible but unverified and carries its own political durability questions. Neither side has a clean win on the scaling question, because the key variables, yield trajectory, tool procurement success, subsidy continuity, are not publicly documented. This is the round that carries the weight, and awarding it requires a judgment call. The evidence does not fully support in either direction. 3 specific challenges could make the verdict wrong here, and they deserve naming before the ruling lands. First, the verdict assumes process knowledge compounds into capacity, but that assumption has not been tested at the volumes where deep ultraviolet multi-patterning's throughput constraints become prohibitive. Hua Hong has demonstrated a working recipe. It has not demonstrated a cost-competitive, high-yield process at the wafer volumes where economic comparison with SMIC, let alone TSMC, becomes meaningful. If yields collapse at higher throughput, the process knowledge advantage is real but dormant. Second, the Biren customer relationship is the most concrete validation signal for Hua Hong's process quality, but no independent benchmark of Biren chips produced on this node has been published. The company's own performance claims for its graphics processor products have previously exceeded what independent testers have measured, until a third party runs silicon off Hua Hong's 7-nanometer line and measures it against the node's claimed specifications. The quality of the process remains the company's own assertion. Third, the equipment access question has no clean resolution. Deep ultraviolet tools below the export control threshold can still be procured, but ASML's servicing and spare parts relationships in China have been progressively restricted. A fab that scales its 7-nanometer line significantly will need more tools and more service capacity than a pilot line does. Whether that procurement pipeline holds over a multi-year ramp is a geopolitical variable, not just an engineering one, and it is the one constraint that Hua Hong's engineers cannot solve by being skilled. All three challenges are real. None of them reverse the core finding. The knowledge exists. It has been independently replicated. The hard constraint that export controls were designed to enforce, preventing China from acquiring the knowledge to execute this at all, has already been defeated at Hua Hong. The remaining constraints are real, but are second-order problems. They can be mitigated. The knowledge gap, by contrast, could not have been once it had closed. Round 3 goes narrowly to the bulls on that basis. The ruling is this: Hua Hong's 7-nanometer line is not a second front in any supply chain sense that matters in 2026. At several thousand wafers per month, it is producing pilot quantities that the market will not feel. The skeptics are right about the numbers this year, and that round was correctly awarded to them. But the contest was never really about this year's wafer counts, even when the framing sometimes suggested otherwise. The contest was about whether the recipe could be independently derived and confirmed, whether the knowledge could escape the single cleanroom at SMIC where it first appeared. It has escaped. Hua Hong's line is evidence that China's 7-nanometer capability is not a one-facility phenomenon that a targeted disruption could neutralize. That is the finding that matters strategically, and it belongs to the bulls on narrow but durable grounds. The restriction was designed to make the question unanswerable, to prevent China from acquiring enough process knowledge that a second derivation was even possible. Instead, the restriction appears to have concentrated engineering talent and state resources on exactly that problem. Hua Hong's new line is what a policy backfire looks like when it is still too small to register in quarterly reports. Hua Hong started this cycle as a mature node specialist, producing the analog and radio frequency components that fill every electronic device below the leading edge. It ends this cycle as a second node on a contested map. Whether that position grows into a real supply alternative or stays a well-funded science project depends on variables, yield, tooling access, subsidy continuity, that the next 2 years will answer. The fab exists. The recipe exists. The scaling is the only open question, and open questions in this industry have a way of getting funded. China does not need to match TSMC's volume to have changed the strategic calculation. It only needs enough supply diversity that no single point of leverage can close the gap it spent a decade opening. The round this analysis awards to the skeptics is the volume round. Several thousand wafers by end 2026 is a pilot, not a front. If you think that framing underweights how quickly Chinese fabs have historically scaled once they have a working process, make that case in the comments. The counter evidence is welcome, and if it is strong enough, it changes the verdict. If this breakdown landed differently than you expected, subscribe and turn on notifications. The next one goes deeper on what SMIC's own yield numbers tell us about where the ceiling actually is.